Hi everyone, my name is Hyung-Sik Kim from Seongyungan University. Today, I'm very happy to introduce some of my recent research results about decentralized machine learning. Recently, decentralized machine learning has received much attention. However, we cannot use this technology without addressing the privacy issue. In this talk, I will present several research challenges that need to be addressed for developing privacy-preserving decentralized machine learning. As you know, data is really important for machine learning. We need to collect well-organized and well-labeled data set to train a model. The standard setting in machine learning considers a centralized data set processed in a tightly integrated system. However, real-world data is often decentralized across many parties. For example, in IoT applications, data are collected from many different IoT devices. Why can't we centralize the data? There are two reasons. First, sending the data may be too costly. Self-driving cars are expected to generate several terabytes of data every day. Some wireless devices have limited bandwidth and limited power. Second, data may be considered too sensitive. We see a growing public awareness and regulation on data privacy. For example, in Europe, the GDPR has become a serious issue to guarantee user privacy. In general, data is resided at the user side, not seen by server. This is our ultimate goal to protect user privacy. There are two popularly mentioned techniques in decentralized machine learning. The first technique is called federated learning. The second one is called split learning or split neural network. Okay, now I will present the key idea of federated learning. Federated learning is introduced to address the following two issues. The first goal of federated learning is to address privacy issue. Therefore, model parameters will never contain more information than the raw training data. The second goal of federated learning is to address network overhead. As you know, to deliver raw data from client to server, high network bandwidth is required. To reduce this network overhead, instead of delivering the raw data, we can just train a model locally and deliver the model parameters only. This is because the size of the model is generally smaller than the size of raw training data. This is our key idea of building a federated learning. Let's see how federated learning works. Server just create local copies of machine learning model, and then server distribute this copy to client devices. And then client train each model with its own local dataset. And then client finally upload model parameters to the server. In this step, we can see that raw data cannot be rebuilt. Raw data is just resided at client side. Client just deliver the model parameter only. Finally, one round is finished. And we know that server does not need to access the localized data. This is just one round description. If we repeat k times this process, we can train the model using federated learning technique. Okay, what characteristics does federated learning provide? In the federated learning, entire model is trained by client. Client access the entire model architecture, and client train the model in parallel, regardless of the server and other client. Interestingly, federated learning can be applied to any machine learning model architecture, such as CNN, RNN, and LSTM. However, there are several challenging issues to use federated learning. The first challenge is non-IID, which stands for independent and identically distributed. This means that the data generated by each client are quite different, and it is also imbalanced. Some users produce significantly more data than others. The second issue is that data are massively distributed. That is, the number of clients would be greater than the average number of training samples on each device. The third issue is the limited communication. There is unstable mobile network connection. The fourth issue is the exposure of private data. I know, in federated learning, a raw data set is not revealed. However, model parameters can still reveal users' private data. The last issue is the robustness against malicious parties. In this setting, maybe there are some malicious parties at the client side. In this case, malicious parties can try to perform poisoning attacks. Okay, to understand federated learning, we need to first understand deep learning model training. For a training data set containing n samples xi, yi, where I is greater than or equal to 1 and less than or equal to n, our training objective is to minimize the function fw, where fw equal to 1 over n sum I equal 1 to n fiw. Here fiw is the loss function on example xi, yi. In practice, deep learning optimization relies on a stochastic gradient descent method through a small subset of training samples. Instead of using n and total samples, we can just use a small subset to speed up the training process. In this case, the model parameter wn plus 1 can be calculated wn minus gamma delta f wn semicolon xi, yi. Okay, in the view of a training deep learning model, we can implement federated learning as follows. For efficiency, at the beginning of each round, a random fraction C of client is selected. Instead of using all client, we want to speed up the process. Also, we want to minimize processing time and communication overhead. And then the server send the current model parameters to each of these clients. This process is very similar to a stochastic gradient descent method. Suppose that n training samples are distributed k client, where pk is the set of indices of data point on client k, and here nk is the number of pk. For training objective, we want to minimize function fw, where fw equal sum of small k equal 1 to k and k over n times fkw, where fkw is defined as 1 over nk sum of fiw. Okay. In this context, we can implement federated stochastic gradient descent method. A randomly selected client that has nk training data samples in federated learning, which is similar to a randomly selected sample in traditional deep learning. So, based on this idea, we can implement federated stochastic gradient descent method. A single step of gradient descent is done per round. At each round, a C fraction of clients are selected. When C equal 1, full batch or non-stochastic gradient descent method is used. When C is less than 1, we just use a stochastic gradient descent method. For example, when c equals 0.5, we can just use 50% of client contributing the federated learning training. I want to present the details of federated stochastic gradient descent. But there are several notations. We use gamma to denote, to represent learning rate, and we use symbol n to represent total number of samples. We use capital K to represent total number of clients, and we just use NK to represent the number of samples on a client K. With those notation, we can describe a federated stochastic gradient descent. In a round T, the central server broadcasts the current model WT to each client. Each client K compute gradient GK like this on its local data. In this case, there are two different approaches to implement this step. In the first approach, each client K submit gradient GK directly. The central server aggregate the gradient to generate a new model. WT plus 1 is computed from WT minus gamma FWT. This can be computed as WT minus gamma sum of NK over N GK. In the second approach, each client K compute WT plus 1 K as WT minus gamma GK. In this case, the central server performs aggregation to compute WT plus 1 like this. The sum of NK over N WT plus 1 K. We can also use a federated averaging technique. We use the same notation. In this case, in a round T, the central server broadcasts the current model WT to each client. Each client K compute gradient GK as FKWT on its local data. In the second approach, each client K compute for E epochs instead of using just one single epoch to compute WT plus 1K. In this case, the central server performs aggregation as follows. WT plus 1 is computed from the sum of NK over N times WT plus 1K. Okay, I just presented the key idea of federated learning. However, if we use federated learning, there is some issues about privacy leak. As I already explained, we can just deliver model parameters instead of raw data set. At the first glance, it seems secure, related to privacy issue. However, still there is some possibility of privacy leak from model update. If we have two model parameters at iteration t and iteration t plus 1, maybe some curious server can try to analyze the difference between the model parameters between two models. In this case, model update can leak information about training data. Because this difference can be calculated as the sum of gradient based on a batch of data. So malicious participant or server has white box access to model update. In this case, definitely it is challenging to protect low data confidentiality against such attacker. Okay, here is another decentralized machine learning model called split learning. This idea is simple. We just divide model into several parts. In this example, we just divide the model into two parts. So the first part is located at client side. The remaining part is resided at the server side. So client just train the model with the first half part. In this case, probably after processing the first half part, some activation outputs are produced. Client just deliver these activation values to the server. We can see that in this model, there is no leak about the raw data set. So activation value is processed with the remaining machine learning model part. And then the server finally updated the gradient value, and then it is delivered to client. This process is repeated with the next client. And next, we repeated this process with another client, and we repeat this step with another client. So finally, one round is finished. Okay, in split learning, a sub-network is trained by each client. Client do not need to have knowledge of the other network part. Client train the model in sequential. This is different from federated learning. In the federated learning, client train the model in parallel. And also, split learning has some limitation. Split learning is currently only applicable to vertical splittable model architecture, such as CNN. There are several deployment strategies for split learning. Client and server just divided. We call this simple vanilla split learning. And also, client has just label and the last layer. In this case, we call this split learning without label sharing. And also, we can use multiple clients As I already explained, we call this split learning for vertically partitioned data. Okay, can you use this split learning idea to protect user privacy? We develop a split learning model for one-dimensional CNN to detect heart abnormality. We analyze the amount of the privacy leakage from the split learning model. I want to produce our concluding remark. Unfortunately, split learning alone is not sufficient to prevent privacy leakage. To address the privacy leakage, we need to consider the following countermeasure. The first strategy is to add more hidden layer before splitting. The second idea is to apply differential privacy at split layer activation to introduce some noisy data. Here is our another observation. Both techniques come with a cost of accuracy reduction. Perhaps this is bad news. If you are interested in the details of applying a split learning for privacy, please read the following paper. Can you use split learning on 1D CNN models for privacy preserving training? Here are some results about privacy leakage analysis. We can see that there is some strong correlation between low input data and the output from the second convolution layer. They look very similar. Actually, when we analyze the distance correlation between those values, we can see there is high distance correlation between low input and activated output, indicating that split learning is not sufficient to protect the confidentiality of low input data. Okay, if we add more hidden layer, can it protect user privacy? Surely, the use of a high number of hidden layers can significantly degrade the model accuracy. Model accuracy can be degraded if we add a number of hidden layers before splitting. However, the effect of hidden layer is limited to mitigate privacy leakage. If we add 8 hidden layers before splitting, distance correlation is still high. Our second idea is to apply differential privacy. Basically, we use the Laplace differential privacy mechanism on the split layer activation. In this case, luckily, we can see that differential privacy is quite effective in mitigating privacy leakage. However, detection accuracy significantly degrade. This is bad news. It means that we can just use a small amount of noise without degrading the model accuracy. So our goal is to find some proper range of noise for the differential privacy. If we divide the model for split learning, so this part is located at client side and the remaining part is located at server. Attacker can implement some reconstruction attack to reconstruct raw data. So when attacker obtain this activation value from the split layer, attacker can try to reconstruct original raw data by using the mirror imaged client model like this. In this case, when we use a differential privacy, we found that epsilon for differential privacy should be greater than 100 to maintain model accuracy. If we increase noise in this case, we can see that model accuracy significantly degrade like this. So this result indicate that epsilon for differential privacy should be greater than at least 100 for accuracy. And also we can see that maybe if we reduce epsilon, if we reduce noise, which indicate that epsilon is greater than 500, some raw data information is revealed. So with those two results, we can see that epsilon should be between 100 and 200 for both accuracy and privacy. From the CIFAR-10 dataset, we can get similar result. Epsilon should be greater than 100 for accuracy. However, for privacy, epsilon should be less than 500. It means that epsilon should be between 100 and 200 for accuracy and privacy. Okay, I also analyzed the pros and cons of federated learning and split learning. Surely there are own pros and cons for each decentralized machine technique. Split learning, for example, split learning outperforms federated learning in terms of convergence speed. When the number of clients is 50 or 100, we can see that split learning converges faster than federated learning. If we want to know the details of those results, please read this paper. We conducted some experiment with real Raspberry Pi and network router. This is a demo, but I want to skip. We can also compare several overhead between split learning and federated learning. In terms of time overhead, federated learning uses much less training time. In communication overhead, federated learning has extremely reduced communication overhead. In the amount of used memory, split learning has relatively less memory usage. This is straightforward because split learning only train on a subset. In energy, federated learning uses less energy. In peak power and temperature, federated learning has higher peak power, thus higher temperature. So those results show that federated learning and split learning has its own pros and cons. So we propose a new decentralized machine learning model by combining the idea of split learning and federated learning to exploit the advantage of each. If you want to know the details of this new decentralized machine learning model, please read this paper. Those graphs show that our new split federated learning model is comparable with split learning in power consumption and memory usage, but more efficient than split learning. Okay, here are concluding remarks. Decentralized machine learning model, such as federated learning and split learning, becomes a new research trend. However, it is not easy to address privacy concerns even with decentralized machine learning technique. So I tried several privacy-preserving techniques to address this issue. However, it is still challenging. So we need to develop more advanced decentralized machine learning model technique. Thank you.